All right, more programming. So in my last video, let me adjust this a bit. In my last video, I had said that I was going to loop back through some Simply Scheme stuff before trying to do more SICP stuff. Because Simply Scheme is an easier book. I've looked at it before. I've worked on some of the problems, but it's been a while, and I was getting kind of stuck on SICP. So, and I looked at the index, and I was like, well, we're working on like trees and tree recursion stuff in SICP now, and this has trees. So I'll look at that, and then I noticed that it was talking about the content of chapter 17 some in there. So I figure, well, let me start with 17, work my way through 18, see if I can do that. By the way, I found on GitHub a definitions file for Dr. Racket that for Simply Scheme specifically that somebody made that seems to work pretty well. It seems to produce like approximately the right output that's expected. So yeah, I'll try to remember to put a link to that in the description. I should keep like a running notes file like Elliot does on his videos of like things to put in the description. Anyway. All right, so chapter 17 lists. Suppose we're using Scheme to model an ice cream shop. We'll certainly need to know all the flavors that are available, and they have a list. For example, here's a procedure that models the behavior of the salesperson when you place an order. So I pasted this into my definitions file, and I screwed up because I didn't indicate, well, I didn't use this quote mark. And so what happened, because you need this to tell Scheme, like, don't try and evaluate this, because you see that's what happened is it's like, you know, we defined a program order, but then, you know, when I just did order vanilla, it's like, okay, so the interpreter's like, I found order, but I can't find vanilla. What are you doing? So then I fixed that, said order quote vanilla, and it produces the desired output, which is because the flavor that I typed is in the list, it says coming right up. And that's basically the model of this ice cream shop is I put in an order and it's one of the ice creams in the list, which is like the ice creams that they have, then it'll say coming right up. Whereas if I say order, let's see, coconut, which I love, then it says sorry, and it actually returns the flavor. You say sorry, we have no coconut, which happens a lot to me in life. So sorry, we have no coconut. Went back to chapter 5 and looked up because I'm like, wait, I know, like I knew the quote would make it work, but I was like, wait, but why do we need the quote? What's the quote do? And I skimmed this a bit, and I think I got the idea. I might look at it more again later, but trying to, you know, do a more problem-based looking up of things as opposed to just trying to read stuff straight through. So, okay, so let's jump back to 17. Back to the ice cream. So, what happens if we want to sell a flavor like root beer fudge ripple or ultra chocolate? We can't just put those words into a sentence of flavors, or a program will think that each word is a separate flavor. Yeah, you'd have like the beer flavor or the ultra flavor. Beer ice cream doesn't sound very appealing. I'm sure somebody's made it though. It does sound disgusting. What we need is a way to express a collection of items, each of which is itself a collection, like this. vanilla, ultra chocolate, Heath Bar Crunch. That's pretty good. Ginger, Cherry Garcia. Somebody likes Ben and Jerry's. That's unsurprising given where this guy taught. This is meant to represent 5 flavors. Right, so this is meant to represent 5 flavors, 2 of which are named by single words, and the other 3 of which are named by sentences. Luckily for us, Scheme provides exactly this capability. The data structure we're using in this example is called a list. The difference between a sentence and a list is that the elements of a sentence must be words, whereas the elements of a list can be anything at all. Words, #t, procedures, or other lists. Another way to think about the difference between sentences and lists is that the definition of list is self-referential because a list can include lists as elements. The definition of sentence is not self-referential because the elements of a sentence must be words. We'll see that the self-referential nature of recursive procedures is vitally important in coping with lists. Another example in which lists could be helpful is the pattern matcher. We use sentences to hold known values databases such as this one. Front your mother, back should know. This would be both easier for you to read and easier for programs to manipulate if we used list structure to indicate the grouping instead of exclamation points. We remarked when we introduced sentences that they're a feature that we added to Scheme just for the sake of this book. Lists, by contrast, are at the core of what Lisp has been about from its beginning. When we introduced words and sentences, we had to provide ways to take them apart, such as first, ways to put them together, such as sentence. Now I'll tell you about selectors and constructors for list. The function to select the first element of a list is called char. The function to select the portion of a list containing all but the first element is called cdr, which is pronounced cdr. They are analogous to but first and but first for words and sentences. Of course, we can't extract pieces of a list that's empty, so we need a predicate that will check for an empty list. It's called null and returns true. Yeah, did I say #t earlier? True for the empty list, false for anything else. This is the list equivalent of empty for words and sentences. There are 2 constructors for list. The function list takes any number of arguments and returns a list with those arguments as its elements. Let me see. 2 and 3 get evaluated as 5, squash, true, another list, procedure, for zucchini. Yeah, it makes sense. The other constructor, cons, is used when you already have a list and you want to add one new element. Cons takes 2 arguments, an element and a list, in that order, and returns a new list whose char is the first argument and whose cdr is the second. There's also a function that combines 2 elements of 2 lists into a larger list. Get back the word append. Okay. It's important that you understand how list, cons, and append differ from each other. List, I am the walrus. So, function list takes any number of arguments and returns a list with those arguments as its elements. And it if it doesn't flatten the lists, it doesn't right, so if you have list it doesn't like, if you pass a list, it doesn't look inside the list, take out the elements, and put them into a bigger list. It just drops the whole list in there. Like this makes a list, but then we see the list is just there as a list. Whereas, so cons, let's say about cons. This is when you already have a list and you want to add one new element. So I am the walrus. All right, so taking a bit of a step back, let's get a little spun around because lists and sentences are very similar. It's just in Scheme, it's just an issue of like lists can be any sort of data, whereas sentences have to have words in them. But it can get a little confusing when you're talking about, because like I think it's reasonable to say like every sentence is a list. It's just a particular kind of list. It's a list of words. Whereas not every list is a sentence. Like this list is not a sentence. Got it. Yeah, an integer, and a truth value, and another list, and so on. I just needed to get that straightened out in my head because when I was starting to talk about like the differences between list, cons, and append, I was like, wait, should I be talking about these as like lists or sentences? I wasn't really sure. But these examples, you could talk about them either way, and it's fine. I think. Getting back to this, so list just basically takes the stuff that you pass it as it is into a new list. So we have two, either you could say a list of words or sentences, either one. I am and the walrus, and it puts these inputs into a list as, again, as lists or sentences. I am and the walrus. It doesn't do anything. It doesn't like process them in any way. It just kind of dumps them into a list. Cons is used when you already have a list and you want to add one new element. It takes an element in a list in that order and returns a new list whose car is the first argument and whose CDR is the second. So car is like the first, and cooter, I'm trying to say cooter, is like, all but the first. So kind of like the rest. And so I gave cons some example inputs, and you can see the last one. Well, let me just work through it. So when I gave it a single word, list is the first element and a list is the second. It outputted the first word as still a list, and then the second argument, which it expects to be a list, as like just some words, like not in a list anymore. Like it kind of flattened the list, that part of it. And then if you give it like a word, I'm gonna use the word and sentence stuff. If you get like a word in a sentence, then you get another sentence that's all on like the same level, which, given that the structure is that it takes two arguments, an element and a list, and like that output kind of makes sense to me. Because like a reasonable program to have is like you have something that takes like a bigger data thing and like a small single thing of data and sticks them together all on the same level, like with no nesting. And so like that's what this does if you give it these particular inputs. I thought this was interesting with this little dot here. Because what did I do? I sort of did it, I gave it, oops. Hey Siri is like the, oops. I gotta not refer to it when I'm talking about it because then it just triggers it again. It's like the new annoying thing that I deal with in life is just the voice triggering of it. But I don't want to turn it off because I like that functionality in certain cases. Anyway, so in this example, I sort of gave it the like backwards output compared to what I think you're supposed to give it. Because like here, I gave it an element and a list, and here I gave it a list and an element, and it gave this sort of weird result where there's like this dot here that I don't know I don't know what this is doing. Like, what's this dot about? Does anybody know? Like, what's the dot? Okay. And then I also, and then the last thing I did isn't actually very interesting. It's just like a variation on the book example. But yeah, one should play with these things in general and see what they do and how they beep when you poke them with different inputs. So that's some sense of how cons works. And then append combines elements of two or more lists into a larger list. And so that's going to be a flattener sort of thing. Like, right? Puts all stuff all on the same level. I wonder though, what happens if we put like another set of, oops. Yeah, okay. So it flattens like one level of listiness, but if you have like a nested list, it won't pwn the nestedness. But it takes stuff one level out of like the Russian nesting dolls of lists. Okay. So when list is invoked with two arguments, it considers them to be two proposed elements for a new two-element list. List doesn't care whether the arguments themselves are words, or lists words, or anything else. It just creates a new list whose elements are the arguments. In this case, it ends up with a list of two lists. So this is good that he's going through them, and I already went through them, so I can compare. Cons requires that its second argument be a list. Cons, although that's interesting because it says requires, but it did output this thing, like it did an error. So that's interesting. Well, since I'm talking about, let's read the footnote. This is not the whole story. See the pitfall section for a slightly expanded version. Is it in this pitfalls? Oh, and it talks about this. See, this is, yeah. So I'm happy with how I'm approaching this chapter because I'm poking stuff and I'm anticipating what the book is talking about as opposed to sort of having it hold my hand as we go along. So that's good. Just as we mentioned about the names word and sentence, resist the temptation to use list as a formal parameter. We use LST instead, but other alternatives are capital L or SICP for sequence. The list constructor cons, here we go, does not treat its two arguments equivalently. The second one must be a list, must be the list you're trying to extend. There is no equally easy way to extend the list on the right, although you can put the new element into a one-element list and use append. If you get the arguments backward, you're likely to get funny-looking results that aren't lists, such as, yeah, okay. The result you get when you cons onto something that isn't a list is called a pair. It's sometimes called a dotted pair because of what it looks like when printed. It's just a printed representation that's dotted, however. The dot isn't part of the pair any more than the parentheses around a list are elements of the list. Lists are made of pairs. That's why cons can construct lists. We're not going to talk about any pairs that aren't part of lists. So you don't have to think about them at all, except to know that if you dots appear in your results, you're consing backwards. Okay. So the issue is acknowledged. He doesn't really go into detail about what's going on. That's okay, though. All right. Right. So where were we? Okay. Cons will extend. Right. So cons requires that its second argument be a list. Cons will extend that list to form a new list, one element longer than the original. The first element of the resulting list comes from the first argument to cons. In other words, when you pass cons two arguments, you get back a list whose car is the first argument to cons and whose CDR is the second argument. Thus, in this example, the three elements of the returned list consist of the first argument as one element, followed by the elements of the second argument. You may be wondering why anyone would want to use such a strange constructor instead of list. The answer has to do with recursive procedures. Hang on for a few paragraphs. Okay. Finally, this is pretty. I like diagrams. Finally, append of two arguments uses the elements of both as elements of its return value. Right, so that's what I was talking about, like flattening. Like it matters. It matters for the output whether it's treating the arguments as elements or whether it's looking inside. Whether the procedure is treating the arguments themselves as elements that are complete or whether it's looking inside the arguments to find elements. And that's why you get different outputs with these. Pictorially, list creates a list whose elements are the arguments. Cons creates an extension of its second argument with one new element. All right, so this is interesting. So I've got this praise function here, and basically you give it a list of flavors, and it'll say that they're all delicious. And so the way this program works, basically, so we have car, and that's selecting like an element from the list of flavors that we give it. So you can see here, And you need, by the way, you need at least 2 flavors. You need at least 2 flavors because car expects to be selecting an element from a list that has more than one. That's just the way it's set up. So if you only pass it one value, it's going to complain, it's going to error. So car selects the first element from the list, which in this list would be ginger. And then SE makes a sentence out of that element with the other sentence, is delicious. So it combines the name of the flavor and the is delicious. And then cons is used to add the form sentence, say ginger is delicious, to a list. Now that's where it starts to get tricky because that list isn't like finished forming yet because there's like a recursive function call here. But it's adding it to a list. And then what happens is you have this recursive call. This call is calling CDR flavors, so basically the rest of the flavors. We see the use of car in CDR. So the first thing we called was, with car we got ginger. And now we get a recursive call to the praise procedure function with the rest of the flavors. So ultra chocolate, lychee, rum raisin. And so that goes in. And we have to, do the analysis again. So then we're a layer deep in the function. We're going to get car flavors. I guess I should say cooter instead of CDR, right? So car flavors, it's going to be ultra chocolate, is delicious. Sentence out of that is going to get added to a list. And so you're going to go around again a couple times until you get to rum raisin. And then so let's just skip to that. So rum raisin, we're gonna have, it's gonna be selected by car. A sentence is gonna be made from it. It's delicious, and then it's gonna get consed to a list, and then you can have the recursive call to praise here. And that's where it gets weird, right? Because it's like, okay, so recursive call to praise, CDR flavors. But now there's nothing left to select. Because if we do, right, so what happened? So we cooter flavors when there's just rum raisin left. Now note, that rum raisin was a list inside of a list. So a couple of open parens over here. Now if we cooter that where rum raisin is a nested list and it's the only element, then we get just like an empty list. And if we do null on that expression, it returns true. And likewise, if we just do null on an empty list directly, it returns true. So when we get to this point, where rum raisin is, you know, the thing being considered, then this test is going to return true. And that's going to be our base case. Now, what's interesting, so if you cons the anything, so I just put hat, because hat is sort of like my foo, and an empty list, then you get a list with that thing as an element. Or yeah, you can cons something in an empty list. And that's why this works. Because like if consing an empty list produced an error, then we couldn't write the program this way. Okay. So because our base case would be an error. But because we can cons with an empty list, then we basically, we cons the first flavor, we cons the next flavor, we cons, and so on and so on. And then at the end, we basically cons the last element and an empty list. And so that, basically adds the last element to the list of lists. Because that's what we ultimately get, is a list of lists. Let me just do that again at the bottom here. Right. So you see, this is a list. Nope. So this is a list, and so is this, and so on. And then they're all inside of a big list. And cons is basically adding each sentence that's being made from the selection of the flavor and adding is delicious into a sentence to this list of lists. So that's how it works. So in this example, there's a list of sentences. That is, the result is a list that includes smaller lists as elements, but each of these smaller lists is a sentence in which only words are allowed. This is the example worth 1,000 words that we promised to show why cons is useful. List wouldn't work in this situation. You can use list only when you know exactly how many elements will be in your complete list. Here, we are writing a procedure that works for any number of elements. So we recursively build up the list one element at a time. Right, list added like a specific number of things that you were inputting. It didn't add like, a thing to an existing list. So yeah, I can see what they mean. You couldn't use it in the same way. In the following example, we take advantage of structured lists to produce a translation dictionary. The entire dictionary is a list. Each element of the dictionary, a single translation, is a 2-element list. And in some cases, a translation may involve a phrase rather than a single word. So you can get 3 deep in lists. All right. So we have this translation program. And how you make it work is you pass it, you call it, and then you give it a word. And internally, what it's doing is it's taking the word, and it's also taking this list, which is basically a very small dictionary, using a French dictionary, English to French, and it's giving it to this lookup function. So we go to this lookup function. We've got lookup, and then the word you're looking up, and then the dictionary, which again is this thing. And so if you just pass it an empty list. Or actually, if you pass it something that's not in the dictionary, it asks you in French again, I'm thinking, if you speak English. And it goes through, I've turned a trace on these functions. So it goes through the whole dictionary until it can't find anything. And then if it can't find a match, it spits out that error message. Or not error message, but that it gives that output, that result. Parlez-vous anglais? Now, as it's going through the dictionary, though, what it's doing is it's taking your word and it's so like say we do give it, say we do give it hat. And what it's doing is, okay, so saying equal hat, and then the first element of the first element of the dictionary. So, and you need both cars there, because the one car will just select this, but then you want to select this thing specifically in order to see if it equals your word. And then if it does, then you return this. And what this is going to mean, so this gets called first car dictionary. So you call this whole thing. And then cdr will return the second element, which is this. That's what would happen. That's what happens if we, like, let's just, right. So when we just did window, translate window, that was the process. It did equal word car, so it checked whether the word we gave it was equal to this, and as it was, it did car cdr, so it first selected this, and then it selected the second element. Now, with hat, since hat isn't window, then we go to else, and what we do is we basically do a recursive procedural call to look up with the rest of the dictionary minus the first element, because we don't want that first element anymore. We already checked it. And so we want to start looking at the rest of the dictionary. And then the process repeats itself. We're going to check the word against book. We're going to check it against computer. We're going to check it against house, and so on until we get to the end. And then when we get to the end, it's going to be like the last example with when we're down to one element and then we recursively call and we cdr that, then when we check if it's null, the answer is going to be true, the value is going to be true, and so then we'll output this. So, by the way, this example will help us explain why those ridiculous names car and cdr haven't died out yet. In this not so hard program, we find ourselves saying car, cdr, car to refer to the French part of the first translation in the dictionary. Let's go through that slowly. Car dictionary gives us the first element of the dictionary, one English-French pairing. Coulter of that first element is a one-element list that is all but the English word that's the first element of the pairing. What we want isn't that one element list, but rather its only element, the French word, which is its car. This car of Coulter of car business is pretty lengthy and awkward, but Scheme gives us a way to say it succinctly. Kadar Dictionary. In general, we're allowed to use names like CD, A, D, R, up to 4 deep in A's and D's. That one means Coulter of Coulter of Coulter, Coulter of something. Or in other words, take the Coulter of the Coulter of the car, the Coulter of its argument. Notice that the order of letters A and D follow the order in which you'd write the procedure names. But as always, the procedure that's invoked first is the one on the right. Don't make the mistake of reading CADR as meaning first take the car and then take the Coulter. It means take the car of the Coulter. The most commonly used of these abbreviations are CADR, which selects the second element, CADDR, which selects third, CADDDR, which selects the fourth. Okay. You've probably noticed that it's hard to distinguish between a sentence, which must be made up of words, and a list that just happens to have words as its elements. The fact is, sentences are lists. You could take car of a sentence, for example, and it'd work fine. Sentences are an abstract data type represented by lists. We created the sentence ADT by writing special selectors and constructors. Abstract data type, I see. That provide a different way of using the same underlying machinery, a different interface, a different metaphor, a different point of view. How does their sentence point of view differ from the built-in scheme point of view using lists? There are 3 differences. A sentence can only contain words, not sublists. Sentence selectors are symmetrical front to back. Sentences and words have the same selectors. All these differences fit a common theme. Words and sentences are meant to represent English text. The 3 differences reflect 3 characteristics of English text. First, text is made up of a sequence of words, not complicated structures with sublists. Second, well, actually, you could have like bullet points and nested points, but yeah, I get the idea. Second, in manipulating text, for example, finding the plural of a noun, we need to look at the end of a word or sentence as often as the beginning. Third, since words and sentences work together so closely, it makes sense to use the same tools with both. By contrast, from Scheme's ordinary point of view, an English sentence is just one particular case of a much more general data structure, whereas the symbol is something entirely different. As we said in chapter 5, symbol is the official name for words that are neither strings nor numbers. Okay. The constructors and selectors for sentences reflect these 3 differences. For example, as it so happens that Scheme represents lists in a way that makes it easy to find the first element, but harder to find the last one. That's reflected in the fact that there are no primitive selectors for lists equivalent to last or but last for sentences. But we want last and but last to be part of the sentence package, so we have to write them in terms of the real scheme list selectors. In the versions presented here, we are ignoring the issue of applying the selectors to words. All right, so we see for first, they just car the sentence, but for last, they need to do all this stuff, including, you can tell right here, like there's a recursive call, so that's complexity. And we see that pattern we've seen a couple of times now in this chapter where it's like there's a check for if the coulter of the thing is null, and if it is, then you output one thing. You output the car in this case, because that means that it's like the last, that you're looking for the last element, and if the coulter of the sentence is null, that means you've got it. So then you just output it basically. But if not, then you do a recursive call, and you keep doing those recursive calls until you get to the end. And but first and but last are pretty similar compared to first and last, in that, first was just car on a sentence, but first is just coulter on sentence, so that's pretty straightforward. But then, but last is a more complex recursive call type procedure, which also has an empty list. And we saw that earlier with consing, a recursive call that has the empty list as the output in the base case. So you have the general idea there. So if you look behind the curtain at the implementation, last is a lot more complicated than first, but from the point of view of a sentence user, they're equally simple. In chapter 16, we'll use the pattern matcher's known values database to introduce the idea of abstract data types. Oh, maybe I should look at that. In that example, the most important contribution of the ADT was to isolate details of the limitation, yada yada. Although sentences are represented as lists, they behave much like words, which are represented quite differently. Our sentence mechanism highlights the uses of sentences rather than the implementation. The higher order functions that we've used until now work only for words and sentences. But the idea of higher order functions applies. I just skipped over this because it was mostly talking about chapter 16, which I haven't read recently. Higher order functions that we've used until now work only for words and sentences, but the idea of higher order functions applies perfectly well to structured lists. The official list versions of every keep and accumulate are called map, filter, and reduce. Map takes two arguments, a function and a list, and returns a list containing the result of applying the function to each element of the list. Right. Map square. And this is a bit like the each method in Ruby. You square each number. You make a sentence from each word doubled. You make, this is a little different. Right, because every is making like a sentence using, I guess it's pulling, it's not, well, Right, so map returns a list, which can include other lists, whereas every just returns a sentence. So map, oh yeah, you see, map gets the first entry, the first element of each list, makes a list out of them. Yeah, map, checking if these numbers are even. And then write this map wants a list, but this is just a word, so it beeps if you just give it a word. The word map may seem strange for this function, but it comes from the mathematical study of functions, in which they talk about a mapping of a domain into the range. In this terminology, one talks about mapping a function over a set of argument values, that is. And listians have taken over the same vocabulary, except that we talk about mapping over lists instead of mapping over sets. In any case, map is a genuine scheme primitive, so it's the official grown-up way to talk about an every-like higher-order function, and you'd better learn to like it. Okay. Filter also takes a function and a list as arguments. It returns a list containing only those elements of the arguments for which the function returns a true value. Oh. This is the same as keep, except that the elements of the argument may be sublists and the structure is preserved in the result. Right. So lambda, so basically filter. So we're creating a procedure here with lambda without like defining it with a name, and flavors the formal parameter. And we're basically doing filter, or let me start the other way. So for each, this is our list of flavors. See, it's a list. And then for each flavor, we're gonna, or I should say, so we're gonna check if swirl is contained within one of these flavors, and we're gonna do that for each flavor. That's what filter will do, is it'll do this member. Is swirl a member? Is swirl one of the constituent words of, if you want to say, the sentences within this list? And then if it is, if when member checks for swirl against one of these flavors, the value is true, then it gets added to this list of things, this list of flavors that filter ultimately will return. So let's just verify that, because figuring out how to run scheme on Dr. Racket was serious effort, so I like to use the interactivity whenever I can. Seriously, thank goodness to whoever on GitHub made this update, because the next best alternative would have been figuring out which, I don't know, some ancient version of macOS to run an old version of Dr. Scheme in or something, because yeah, it was a pain in the neck. Okay. So similarly, right, so filter word goes through this list and checks if each thing in it is a word. And if it's not, if it's a sentence or whatever, then that returns false. But if it is a word, then filter puts together a list of the words. And that's why you see this output. So ultra chocolate and raspberry sherbet are not words, they're sentences. Filter lambda nums. This one's a little trickier to follow. Oh, basically, if the first number is the same as the last number, then those are the true values for filter. I got it. Okay. Or wait. First value is the same as the second value, not because that's CADR. Not the last value. Okay. Filter probably makes sense to you as a name, the metaphor of the air filter that allows air through but doesn't allow dirt and so on. Evokes something that passes some data and blocks other data. The only problem with the name is that it doesn't tell you whether the elements for which the predicate function returns true are filtered in or filtered out. But you're already used to keep, and filter works the same way. Filter is not a standard scheme primitive, but it's universal convention. Everyone defines it the same way we do. Reduce is just like accumulate, except it only works on lists, not on words. So accumulate basically, where is it? What does it do? It applies a procedure to 2 words of the sentence, and then it applies the procedure to the result we got back and adds another element and so on. So this is a good example. Makes a word out of A and C, and A and C and L, and then ACL and U. So back to reduce. What happens here is we have multiplication of 4 and 5, which is 20, and then 20 and 6, which is 120. This one's a bit tricky. So first element of the first, so this, what does this do? This makes a list out of the first element of the first list, first element of the second list. The sum of that is one list entry, and then also the sum of the second element of the first list and second element of the second list. So for this part, it would be 1 and 31. And then for this part, it would be 2 and 42. And so then we would have 31 and 42 as like a new entries, elements of a new list. And then those would be combined with this list. So we'd have 31 and 500, 531, and 42 and 600, 642. So it wasn't too hard. All right, I'm gonna call it a video here because I've been going for a while. I think it's gonna take me longer than I thought. As I go along, I wonder if I should actually go through more of Simply Scheme, because I mean, I've been able to look stuff up and get the idea pretty quickly so far, but I wonder, I guess, I mean, I'll still continue with my plan from before of review chapter 17 and 18, and then try and go back to SICP, and then if I struggle again, maybe I'll think about doing more.